I will step a little bit into theory as I'm talking about, as you see, hazard identification. We have to understand a little bit what is behind, so I like to go a little bit into theory. Who finds this boring? You have time, 30 minutes to go out and then come back, maybe then it's more interesting. The very beginning always is we start from a primary stress. The primary stress says my stress distribution goes ahead like shown on this line. So we have parallel stress lines if we are watching just the vertical stress component. If we are then building a tunnel, of course, these stress lines cannot go through anymore. They have to be divided like this one. And as you can see already on this picture, this will cause some higher stress situations on the sidewalls, and this will cause some tension stress in the upper and bottom part in case of my stress situation is like what I have shown here. And at the moment I'm talking just about the vertical stress lines. So if we are watching the same situation in a three-dimensional stress situation, we can say here is our tunnel face, and we have to go through a three-dimensional stress situation, vertical stress, horizontal stress in all the directions. And my tunnel would like to go through here. So what is happening with my stress situation? It will be distributed in this way, and everything, and this is very essential, is happening in a distance of the face, normally 1 to 2 diameters behind the face. This is essential to know because then we understand the film, which I will show afterwards. Why do we have the collapse directly here behind the face? Because we did not put in enough support. From the stress situation, another very essential point of view is what is happening on this specific point. We learned already that here we have a higher stress, and here it could happen that we have a lower stress, maybe tension. So what happens? The one stress which is showing that I call it tangentially. Tangentially means this direction, in vertical direction on this point, is going up to a very high value. And the radial stress, which is the stress in this direction, is going to a 0 value, which is the worst situation which we can imagine, because this is the situation which we have in a uniaxial compressive strength test, which means I have a stress from these sides but no stress from around, and this is the worst situation which we can have. As soon as I put some stress on here, I can put much more stress in the vertical direction, of course, and this goes then to a triaxial stress. But the situation when we open the face is like this one. When we open the face, we have a uniaxial compressive stress situation, and we have to, let's say, get rid of this worst stress situation quite quick before it cracks. And on the upper part, we have a same situation. We can say we have a 0 radial now in this direction, and we have any tangential stress in this direction, but this value could in the worst case go on this side, so then we have a tension. And it is the job of the designer to find the right geometry to have no tension in this situation. But sometimes it's unavoidable if you build a subway, for example, and you need this broad, let's say, geometry, then you cannot avoid to get the tension, but then we have measures to handle that. So if we have now a K1 means my horizontal stress is the same than the vertical stress at the beginning, which is in some regions the case, then we cannot predict where these cracks will start because we have a circular cross-section, as you can see here, and a stress situation from all the sides which is the same. So it's clear that we cannot predict where the cracks will start in case that there will be some cracks, because my uniaxial compressive strength is lower than my stress which I have. In the next situation, my K is not equal to 1. For example, in European regions, we normally don't have K is 1. In Austrian regions, we have a K, let's say, of 0.6 around this one. So it's not equal to 1. 0.6 means we have more vertical stress than horizontal. Yeah, more vertical than horizontal. We have some other, let's say, situations in the fault zones, peri-Adriatic fault zone between Austria and Italy. There are some regions where this is not the case, but most time we have a K of 0.4 to 0.6, which means we have more vertical stress than horizontal. Still in this picture you see we have a circular cross section, but due to that we have more vertical stress than horizontal, my cracks will start in this region. We saw this already on the first slide, that my stress lines go around here, and we have a stress concentration in these areas, so most time we get the cracks started here. Now what happens if we go to an elliptical shaped cross section? We have no circular one, as you can see now. This makes the situation a little bit more complicated, but in principle still we have, if we have no support in, a high vertical stress and a zero of radial stress. So the situation in principle keeps the same, and keeps the same also for the top point here. Why am I not showing the stress situation in this point or these points along here? I'm just speaking of the maximas and minimas. If you are interested in having the stress situation around your underground structure around here, you will be in between these situations between here, and we are always focusing on the maximas if we do analytical calculations. So again, back, we know already here we have the stress concentrations, the tension gets up here. So in an elliptical shaped cross section with a K not equal to 1 and not circular ones, we await the cracks in these regions. What is happening with the material when it cracks up here? It is not loosening its strength to a zero value, and we can see that very good if we look into a shear test diagram. On a shear test diagram, we put up the shear stress on the one axis and the deformation on the other. Yeah? And this means we get a high shear stress until it breaks. Now the rock cracks and breaks, but it does not fall down, as you can see, to zero. It keeps, as we say, a so-called residual value. So we can still count with this material, but not with the maxima in the calculation, but with, let's say, reduced shear stress. And we do that in the so-called plastic zone. I mean, I don't like this name plastic zone very much, because nothing is plastic, but it comes from numerical engineering. And numerical engineers are dominant for the moment, and they say, okay, either it's not plastic or it's plastic. And they brought us this name to the plastic zone. And we had a big fight, by the way, with the Swiss when Kovari was at the ETH in Zurich, that the Austrians called several things with different names, you know, and we said, okay, we follow one guy who is brilliant in that, and they said this is called a plastic zone. Okay, the Austrians now call it plastic zone. What is meant? It is meant that here we have a destroyed rock in. This is a destroyed rock because the stress was too high. The rock could not cover these high stresses within this area. What you see, if you look very carefully at the radial stress gets up and the tangential stress goes down. I jump back once more to the one slide where we had it here. You see, the material cannot take this uniaxial stress situation where we have this very high stress, this direction, zero, this direction. The material was not able to cover that, but it can take a stress situation where you have a very, let's say, sound circumference stress in this direction, which is shown by this stress number here, and the tangential goes down the further you move away from your underground structure. And there is a point where you can where your material can take the stress, which is here the case. It can take this stress and then also this. and will not be collapsed. That's why a plastic zone has a certain depth, yeah? Goes just in like this one, and then we have to carry on with this situation in our design to make the right design measurements to be able to cover this, let's say, deformed and plasticized material. Okay, this means we started from this situation, we came to this situation, at the face we had no support in, but we got a plastic zone. Our job, by the way, is to avoid a plastic zone. It's the same thing then in soil mechanics. I mean, we are speaking of ground failure, but nobody wants to have a ground failure. Our job is to avoid a ground failure. Our job in underground engineering is to avoid this plastic zone. So what do? We put in a support, and this support brings our stress curve a little bit up, because the radial was 0 before, now climbs up to a certain value. This is our support pressure and starts now from here. And this is the job which we have to fulfill to bring in the right value for this support. A very old diagram, maybe all of you know this Fenner-Pacher diagram. What did he find out when he was working in Iran, by the way? They found out that if I allow some movements, my stress concentration goes down. So it is not needed to immediately put in this support. Let's say, wait some time. The question always is how much time, and in tunneling we don't have time. We have to find other measures to speak about time, but the diagram clearly shows if we put in the support, when we have 0 deformation, we will have to carry very much support. By the way, this is not possible because you have to mark out your material, as we have seen in your diagram already, or organigram. So it needs some time to mark out the material, and then we will have some deformation. On the diagram here, you can see the time axis and the deformation. And you see the deformation gets to 0 after putting in some support. This is the so-called support line. We meet the ground reaction curve with the support line, and then this means 0 deformation anymore. And this is our big goal, to have no deformation afterwards. So our big goal is to meet the ground reaction curve at, let's say, a minimum point. Better would be to meet it here, because this means we need the most little support which is possible. If I would bring in my support at this point, I would have to bring in much more support, because I would meet my ground reaction curve here. And this means my pressure, here we'll read out the P, this is the stress. The stress which has to be taken by the support would have been much, much higher if I would have installed it here. So I try to install it down here, because then the thickness of my support can be much thinner than if I compare to install it in front. That's why, by the way, in a machine-driven tunnel, in a TBM tunnel, we need tubings this size. I just was in Germany, Boslar tunnel, 65 centimeter thickness of the tubing elements. Yeah, it's clear. I install my tubing behind the machine immediately, because I need the tubing to move the machine forward, and there are very high pressures on the machine. Here I'm talking about conventional tunneling, where I would like to optimize to make the thinness possible, because this is a matter of cost. Now, the question is, do I need a support? I come then later on to the diagrams, in which rock categories do I need a support and in which do I not need a support. If I have the situation that my rock does not collapse, then I can just reduce my deformation. You see, unsupported would mean 1.5 to 2 diameters behind the face, that I get a deformation of this size. Here we have the delta R, this is the deformation. And if I bring in a support, then I can reduce my deformation to this value, which I can read out here. If there is no need to reduce my deformation from any matter, then I wouldn't put in a support, let's say at the Brenner base handle, where we have 1,800 meters overburden, 2,000 meters overburden. Nobody cares how much deformation do I have, because the cows or animals who are living above, they don't care if they are standing 5 centimeters deeper or higher, you know. From this point of view, I wouldn't need a support there. But there are regions where I need a support because otherwise it would collapse. And this is another point. But just I wanted to figure out that I can put in a support to reduce my settlements, to reduce my deformations if I'm forced by any authority to do so. Now, we have the ground reaction curve again shown here. And now I can choose my support. I can choose a very stiff support. Stiffness is meaning that this line goes up quite steep. And then with this stiff support, I would need quite much pressure in the support. So the support will be a little bit thicker. But the deformation which will occur will be lower. If I put in a very weak support, meaning a Young's modulus which is very low, then I can choose a very thin support, as you can see, because the support pressure can be read out here, but my deformations will be a little bit higher. I can choose a methodology in between. I can say I use a material which has a stiffness which is in between this and this, and then I put in a so-called yielding element which just deforms but doesn't take really stress. And then after a while of deformation, I can put, or it stops to deform because it has a certain length. I will show you that on a slide afterwards. And then my support works with the same Young's modulus than it was before. This was an idea when Austrians had to, let's say, underpass very difficult fault zones, which were called the Kleinarm tunnel, and it was Rabchevich who had an idea how could we come through that, because we had one collapse after the other. And these yielding elements were finally developed then in the year of 2000, around that, because Rabchevich in the 70s just said, keep the shotcrete shell open, because the shotcrete shell cannot take the stress which comes. It will be destroyed. And that's why he said, keep it open, make slots in the shotcrete, but this was not the final solution which we are having now. So what are the typical ground reaction curves? So what are typical, let's say, rock behaviors which we meet in reality? We have a certain stress where we start and it goes down quite linear. So this is a characteristic curve which can easily take the stress situation. Yeah? Imagine you have a granite which can take 260 megapascal uniaxial, and you have a stress situation of 5 megapascal. So the granite can easily take your stress situation. So there will be no risk, even if you don't put in any support. The characteristics curve 2, which, by the way, can be calculated quite exactly if you have the material parameters available. Here it shows it goes already into a plasticity. So the rock is already a little bit destroyed, but will not collapse if you wouldn't put in support there. And in the line number 3, we have a characteristic curve where it says it goes from the linear in a non-linear, which means the rock will be destroyed anyhow. And if you don't put any support in, it will start to raise up with the stress after having reached a certain deformation. So situation number 3 cannot work without any support. It will for sure get a collapse if you don't put support into this line in the right point. And you will put, or you will try to put in your support when you reach your lowest level, because this means lowest or thinnest support which you can imagine. I just have now to differ 2 kinds of support. The one who are passive. Which are the passive supports? So, for example, shotcrete. You put in a wire mesh. You put in a steel arch. This is a passive support. You just react on what is your ground doing. By the way, we would never count on a steel arch in a design, because please compare the moment of resistance of a shotcrete shell, which is just 15 centimeters thick on 1 meter. Compare this moment of resistance with, let's say, a steel arch, moment of resistance of a steel arch, and you will see the steel arch is almost nothing. This is a reserve of safety in the design, but we do not count on that. The ways of doing it are different. Maybe the Swiss do, the Germans I know do for sure, because the Germans are very exact. The Austrians are a little bit in between, you know. We are focusing on what is bringing very much, the rest is still safety. But we do not put it into the calculation. What you see here is a typical quite stiff, let's say, support. This is the ground reaction curve, which we got from the laboratory results, and this is a quite stiff support. This would be a quite weak one, or let's say Young's modulus much lower, which then gives you a result low deformation or a little bit higher deformation. It's to be spoken with your client, what does he accept? If he accepts high deformations, no problem, we will put in a thin support. Why should we have, let's say, a restriction to 5 centimeters of deformation in a 1,000 meter overburdened tunnel? No reason for that. I mean, in the Inntal tunnel, we had 1 meter of deformation radially, 1 meter. Why not? Yeah? There was nothing which could be damaged on the above the tunnel. On the other hand, we have the so-called active support. What is an active support? Bolts, for example. Bolts are active support because I try to raise up my cohesion, my friction angle with putting in an active support. Injections, ground improvement, this is active support. What is the consequence? My ground reaction curve, which was that at the beginning, now gets much better because I put in my very good materials, rock boards, and other things which you put directly into the rock. You really support your rock to carry the load. Here, in the passive way, you just underground, let's say, in the tunnel, and you put in something, shotcrete, whatever you put in, but it's a passive way. We, in our opinion, we need both, the active and the passive. The better is the active, because here you support the rock in the rock already. Just a word to the shotcrete. Shotcrete nowadays gets very high strength after, you see, 24 hours. We get up to 10 megapascal. The shotcrete industry produces much, much higher, let's say, UCS, uniaxial compressive strength. And we always never asked for that. If you get, let's say, a product, however the name is, Sika, BASF, all these, you will get a shotcrete which has already up to, let's say, 40 megapascal within 24 hours. Who needs that? This is what we are asking for. We pay a lot of money into these ingredients, chemicals, but no rock mechanics engineer was with them when they developed that. We are in the opinion it's fully enough to get these, let's say, 10 to 20 megapascal on the shotcrete strength. This is fully enough. Yeah? There is a development in a direction what we or what the rock mechanics engineers never said we need this development. At the end, we get these after, let's say, 28 days, we get these 20 to 30 megapascal of shotcrete. You might know that there is a guideline on shotcrete technology, or in English at least available, which differs the young shotcrete development very good and is, I think, established. By the way, shotcrete can be calculated nowadays quite exactly by the so-called flow rate method. What we often see is that the design consultant fills in a linear elastic material behavior for his calculation. But linear elasticity, we are far away from that in reality. And that's why there was a development going on. How can we really calculate the behavior of this shotcrete? I don't want to step into the details here, just to mention this passive support element. And by the way, shotcrete has to be tested in a little bit other way than is often seen. What we often see is waiting for, let's say, 2 days, and then drill a shotcrete core out of the shotcrete shell. But we are not interested first in what is the strength of the shotcrete after 2 days. We would like to know what is the strength of this material after 1 minute and 6 minutes and 12 minutes and 1 hour, because all this stress redistribution, which we saw, takes place in 1 to 2 diameters behind the face. After 2 days, I'm far away, or hopefully, and then what am I searching for? So, first point. Second point is I drill out the core if this is my shotcrete shell, I drill it in this way. And then I have a sample, and take this sample and put it into the machine in this way. So I test it in this direction. So coming back to the shotcrete shell, I would test it in this direction. This is the best situation which you will have, because you spray your shotcrete on in this direction. So you get your best quality in this direction, but you have no forces in this direction. Your forces are working in the shell perpendicular to that direction. So we would be interested in a sample which is this direction. That's why I brought this slide. We put normally in a machinery directly behind the face, where we can test the shotcrete, let's say, after 1 hour. And we are in the opinion that this helps the designer or the site supervision a little bit more to say something about the quality, compared to drilling some samples after 2 or 3 days out of the shell. Now to the failure mechanisms. Also here I start from the very beginning, because we put everything up in a more Coulomb's diagram, where we can show the uniaxial stress in this circle. The one stress is 0, the other has any value. If we do a test in this situation, uniaxial, let's say this is my sample, and I press it this direction, I have no forces around, it will get a so-called split tensile failure behavior, which you can see here. If I have some stress around, getting a triaxial situation, a stress from all the sides and also from this, I'm a little bit deeper inside my rock already. This would be a stress situation which we see here, a sigma 3 on the one hand side, which is the sidewall pressure, and a sigma 1, which is the vertical on this side. And if we touch the more Coulomb's line, we will get a failure which looks like that one. And of course, there is also a structural failure on the side outside here, which hopefully a tunneler will never see, because this means we have the same stress from here than from here, and close to the underground structure, we will never have a very high stress in this direction and in this direction. This is of interest, of course, for how did the fault zone occur? Why was it possible that a fault zone occurred? Because of earthquakes and all those things, but a structural failure is not in our view. On the left-hand side, you know, the more Coulomb goes quite quick to a 0 point. We could have a tensile failure. Translate these simple things from a laboratory to the real underground structure. So then it's clear that we will get a split tensile failure quite close to the tunnel, because here I'm missing a sigma 3. Then I will get a shear failure deeper inside the tunnel, because I have already a sigma 3 and a sigma 1, and far away from the tunnel I will get a structure failure. But this is not of interest for us. Yeah? So we have to deal these risks, split tensile failure and shear failure. This we have to handle. It was Feder who made really good tests in laboratories where he said, if I have a structured geology like this one, my question is, how can the split tensile failure then reach in? And you see that he found out that this angle I don't want to go into the details, comes from soil mechanics, is the maximum angle where the depth of this will occur. So now I'm coming back to civil engineering. What happens if this is a column and I bring my forces from here to here? It will buckle out. Yeah? The structure, if this is a steel structure, it will buckle out. What do the civil engineers do? They bring up a very low force here and the problem is solved. And what do the tunnelers do? The tunnelers do the same. They bring in a board. Because this board, this is my buckling length, I could say, let's say go to this slide here. This is my buckling length. And this could buckle out this way. To avoid that, already Rabchevich said, please bring in some boards. Yeah? And this reduces my length of buckling and strengthens the material a lot. And this can be done to avoid it. These are just some photos from the tests which Feder did, where he found out how deep does the failure mechanism walk in the different layering situations. And we learn from these laboratory tests, of course. The next effect which we can have is a so-called cherry seed effect, which means that the forces going up here and here will try to move this area inside the tunnel. That's why we say it presses from the left-hand and right-hand side and then shoots in this material which is in this area. To avoid that, we bring up some boards. Same situation, again from a laboratory test, because we often saw in the coal mining that they have the problem that the material buckles up. They do not do an invert, so material comes up, and in the laboratory test it showed perfectly what happens. And what do we do nowadays? If we have this problem, we can bring down some boards to avoid that, or we put in an invert. Same situation if we have the stress, let's say, some layered structure above my underground structure. We learn this from the engineers who build a lot of things with wood. What do? If they have a small wood structure, they climb together, many of them. And then they get a beam which can really take high loads because they are climbed together in all the layers. What does it mean from the stress situation? If you have a very thin layered structure, you have very high stress concentrations because the sigma is always the bending moment divided by the moment of resistance. And now what do? You raise up your moment of resistance a lot because you climb together all these layers. And now you do the calculation again. Sigma is bending moment dividing by moment of resistance, but the value is much higher, so your stress is much lower. So climbing together these layers, we cannot do so easily. We do that by bolting. Yeah? And bolting brings then down the stress. And this avoids then a crack. So just some reasons for that. The split tensile failure could be drawn on a theoretical sketch. There's no need to explain that. But the others is the shear. The shear line goes much deeper into the rock. That's why I brought this slide with me. To give you an idea, here I can handle the problem with quite short rock boards. But if I would like to avoid a shear failure, I need long boards. And it happened, the photo is not very good, but it happened that this shear failure in the Tauern tunnel came in, it was in the 70s, and was then repaired afterwards with very, very long boards. Another effect which we often have is the so-called rock burst. There are rocks available who do not break immediately. They, let's say, store the energy and then explode suddenly. And I brought a small film with me to give you an impression what is a rock burst and is this a dangerous situation, yes or no? Of course, there are rock bursts like this one where we can only take the film afterwards, because if I would be the filmer in, I wouldn't stand here. But a small problem was filmed. Just to give you an impression of that. You see the explosions. The rock explodes here and could hurt a miner. You see the plates then? So it doesn't react for a long time, but then suddenly explodes. And you have to check that in the laboratory if you will meet such a situation. And this can be checked in the laboratory quite easily. Of course, we also put some glasses, kind of glasses around if we expect some samples, most time getting them from South Africa, because this is a quartzite and it explodes at, let's say, a uniaxial compressive strength of about 300 megapascal. And if my laboratory guy would stand beneath, he wouldn't wake up again. So materials which can take very, very high uniaxial compressive strengths are a little bit in danger of being then an area for rock burst, and in the Brenner-based tunnel we await a small section getting this rock burst, not in that dramatic situation like here. And for that, I have to say, a rock board was developed by Atlas Copco, used in the mining industry up to now, not used in the tunneling engineering field. The reason for that is simple: it's much too expensive. What is the rock board doing? The rock board deforms a circular shaped steel geometry by being pulled out through this energy absorber element in a 6 nodes geometry. You can imagine you deform a circular steel into a 6 nodes steel. This deformation from a circular into 6 nodes needs a lot of energy. Yeah? And this is done by being pulled out through this energy absorber element. And you can order, let's say, boards with a length or let's say an energy absorber length, whatever you want. If you say my rock burst will be 60 centimeters deep, then you can order boards which have a 60 centimeter length of being pulled out. Tests are done here. As you can see, this is a very small board, can take 80 kilonewton, typical for the mining engineering, then can take 300 millimeters, and then takes a little bit more, up to 100, and then breaks. There were also some dynamic tests done where kilojoules of 15 were pulled on this board and watched what happens. What is the elongation, as you can see, up to this about 300 millimeters. And then we mentioned on the first slide already, it could happen that we have some tensile strength over this underground structure occurring because of these stress lines. And other issues could be that a fault zone is running through here. What do we do then? We count on this weight and put some boards in to get rid of this dangerous situation. Others could be falling, block is falling down. The geologist told us this is the structure. Then we have to handle such a situation. Sliding, it could slide down. It could be a tipping or a splitting of the rock. Before I go ahead with this, because I split this lesson in 2 parts, we make a break, and Gerard will tell you some other topic, and then I restart again with these issues of how to see or how to understand why situations are risky. Please.